Hello, everybody. Thank you for taking the time out of your schedules to watch my presentation. For my project this semester, I decided to perform an analysis on predator-prey interactions. So what are predator-prey interactions and why are they of interest? Predator-prey interactions are fundamental in understanding the longevity and the stability of an ecosystem. This is due to the fact that the number of individuals within a predator population is directly related to the number of individuals within a prey population. Consider the classic example of wolves and rabbits. Suppose that a wolf population preys on a rabbit population. As the number of rabbits in the ecosystem increases, wolves experience less competition amongst each other and have greater food options available to each other. This results in a greater chance of survival and reproduction for the wolves, culminating eventually in positive growth in their population. However, the rabbit population responds negatively to the increased presence of wolves and will begin to diminish. As the rabbit population declines beyond a certain threshold, the wolves experience too great a population amongst each other, struggle to find food, starve, and overall are less likely to reproduce. This causes an eventual decline in their own numbers, and the rabbit population uses this as an opportunity to recover, eventually leading again to an increased number of rabbits. The cycle simply continues. These relationships are of particular interest to conservationists as they grant us insight into how an ecosystem can be naturally maintained with minimal intervention from humans. Isle Royale is a small isolated island located off the coast of the Upper Peninsula, situated within Lake Superior. It's unique in the sense that its ecosystem is relatively simple compared to other ecosystems. Most notably, it contains just one major predator, the gray wolf, and it preys on a small number of species, moose and beavers. Compared with a far more complex ecosystem, such as Yellowstone National Park, we see a greater variety in the number of predators and a greater variety in the number of prey. The relationship between all of these populations are heavily intertwined, making any sort of modeling far more difficult. The objective of my analysis was to examine the relationship between the population of moose and the population of wolves on the island, and attempt to forecast future population numbers for both populations. My data was retrieved from the Isle Royale Wolf Project, retrieved from a website called isleroyalewolf.org, and it displays annual estimates for the number of wolves and the number of moose on the island from the years 1959 to 2019. Methods I used when describing this relationship include linear regression and an examination of the cross-correlation between the two populations. When forecasting future population numbers, I relied on ARIMA models fitted to both populations individually and a VAR model attempting to predict both simultaneously. A simple linear regression attempting to predict the number of moose based on the number of wolves revealed a negative relationship between the two populations. As the number of wolves increases on the island, the number of moose tends to decrease. However, this relationship is not very strong, as it has a correlation coefficient of just negative 0.34. However, the model does suggest that the number of wolves is a significant predictor for predicting the number of moose on the island with a p-value less than 0.01. However, this may be due to the simplicity of the model itself. It's also worth noting that the model suggests that with every increase in the number of wolves, we observe an approximate decline of about 15 moose on the island. But I personally find this number to be a bit too high, as any given wolf is unlikely to feed on 15 moose in a year, and any new individual introduced into the wolf population as an infant lacks the ability to even hunt on its own. Further examination of the relationship, first by plotting both populations side by side, revealed that generally local maxima in the moose population correspond to minima in the wolf population, and maxima in the wolf population correspond to minima in the moose population. There are some significant differences to be addressed within the populations. Most notably here in 1996, we see a sudden decrease in the number of moose due to many dying of malnutrition, and the fact that the wolves nearly went extinct on the island before being reintroduced in 2019 by humans. Cross-correlation plots reveal, at least for moose and wolf, the moose and wolf series, that future values of the moose population are negatively correlated with the wolf population at any given time. Similarly, past population numbers of the wolf population is positively correlated with the moose population present time. Overall, I would say that this implies that the moose population is a good leading variable when attempting to forecast the number of wolves on the island. The first step in my analysis was forecasting the wolf population. I first performed an ADF test based on the raw data for the wolf population over the years, and it resulted in a p-value of 0.4576, indicating that the data is non-stationary and will need to be different. More on that later. I also plotted the ACF and PACF plots for the wolf population, which demonstrates 4 significant lags for the wolf population, according to ACF, and none for the PACF. Differencing the wolf population and performing an ADF test resulted in a p-value of 0.0305, indicating still that the data is non-stationary, so it differenced once more, and the ADF test resulted in a p-value less than 0.01. This is stationary. So for the ARIMA model, I use integrating order 2. According to AIC selection, the final ARIMA model was an ARIMA 2223. This is the equation for the model with the coefficients as given, and white noise following normal distribution mean 0, the variance 27.86. And over here, we have a plot of the observed wolf population with its forecasted values. The ARIMA model suggests that overall, the wolf population won't change much from 2020 to 2029, but will experience fluctuations in the interim years. I repeated this process again for the moose population. The ADF test for the raw data of the moose population resulted in a p-value of 0.5791, again indicating that this data is non-stationary, again will need to be differenced. The ACF plot indicated more significant lags, but I still, similar to the analysis I did for the wolf population, I consider just the first few years. Differencing the moose population once and performing an ADF test resulted in a p-value 0.0777, again indicating this data is not stationary, so a difference once more, and the ADF test then granted a p-value less than 0.01, which this data again is stationary. So we'll use integrating order factor 2 for the moose population as well. Decided on the same model used for the wolf population to forecast future values of the moose population. With the equation given as follows, and the white noise following a normal distribution mean 0, variance 56,795. Forecasted values imply that the moose population will increase from 2020 to 2029, but again, will experience some minor fluctuations in between. I selected this model via AIC selection. However, this model was not the model with the lowest AIC. That was actually the ARIMA 021 model. However, the forecasted values increased linearly, and this didn't really fit into what we know about the relationship between these two populations. And I found that this model provided more realistic results. So, according to my own discretion, this is the model that I decided on. Just to show you an overall picture of the overall forecasting results for the wolf and moose populations, we see that the moose population is expected to increase, and while it's difficult to see on this scale, the wolf population is expected to remain relatively stable. Forecasting again now, instead with a VAR1 model, equation given as follows, and an intercept term included. We have the fitted values and the observed values for both populations. We could see that the VAR model does a decent job at displaying the behavior of the two populations over time. I take this to mean that the VAR1 model will grant relatively decent forecasting results. And we can see these forecasting results side by side, and it actually displays the opposite of what the ARIMA models suggested. The moose population is to decrease, while the wolf population is expected to increase and then eventually sort of stabilize. This makes more sense given what we know about how the two populations behave. This increase in the wolf population would correspond to a decrease in the moose population. Additionally, displaying this overall figure again, I liked these forecasted results better because we could see that the forecasted values tend to approach the mean value of the two populations. Whereas, again, if you remember, the ARIMA model predicted that the moose population were to just continue to increase. So to conclude, the wolf and moose populations do have a direct effect on one another, while the VAR model produced more accurate results than the individual ARIMA models. However, further analysis is required to really understand the intricacies of this relationship, as there are certainly more complex factors associated in the population fluctuations. So for a future analysis, we can include the data for the Isle Royale beavers, which I had intended to include in my own analysis. However, the data was not published. We could also include further data for more predictors, such as the average lifespan of both species, the predation rate of wolves on the moose, the survival rate of both species. There is also the problem that due to the limited number of moose on the island in general, the limited number of wolves on the island in general, the wolf population suffers from the inbreeding, producing many non-viable offspring, many of which don't survive into adulthood. This would be a significant predictor to include in a future analysis. And lastly, we could simply just include more observations. My data includes only 60 observations taken annually with estimations taken over just a few months span. Perhaps if the data was on a quarterly or monthly basis, we would be able to create more accurate forecasting results and better understand the relationship between these two populations overall. But anyway, thank you again for listening to my presentation. I hope you all learned something, and yeah, take care.